So last time we talked about nil radicals.
Sir, can we find non-zero divisors of infinite?
In a field, do we have non-zero divisors?
Sorry, infinite ring.
Infinite ring. Yeah, so this is from a given ring. Let's say you know a finite ring. For example, a finite ring, example of a finite ring, Zn, right? From this, can you construct a ring which has infinitely many elements using this ring? Huh? Sorry? Yeah, infinite Cartesian product which has or there is another, yeah, Znx. If you put this, right, this is polynomials with coefficients coming from Znx. Do you now this Zn is contained here. This has many zero divisors, right? Yeah.
Sir, actually my doubt was to find the number of.
Number is no. I mean here this will have. Okay, so this is exercise. Find zero divisors of Z. Let's put 6. Okay. Once you know Z6, you can probably do it for Zn. Okay. It's a. I can give you, but that won't. It's better that you try understand that, and then we will discuss this. So we were talking about the nil radical, that is set of all nilpotent elements. So last time we proved that if so let I n be the collection of all x in A, x power n is 0 for some n, then this is contained in P for all prime ideals. So this implies that n is contained in the intersection of all prime ideals. So therefore natural question is whether this is equal, and we try to answer that. So we started by looking at an element x which is not nilpotent. Then we looked at this collection of all ideals such that x power n is not in I for all n. This collection is non-empty because the ideal 0 belongs to sigma. Therefore, this is non-empty, and hence and then we looked at any chain of ideals in sigma, then we proved that this chain has a maximal element, which is the union of I n from 1 to infinity. This belongs to sigma, which means that every chain in sigma has a maximal element, has an upper bound in sigma. Therefore, by Zorn's lemma, there exists a maximal element so let's call that say P in sigma, and we wanted to prove that P is a prime ideal. So, if suppose I have x y being A such that the product belongs to P, we want to say that either x belongs to P or y belongs to P. Suppose both, okay. So, suppose x is not in P and y is not in P, that would imply that this P plus x is an ideal which is bigger than P, therefore, it is not in sigma. That means there exists, this is not in sigma, which means there exists some power n such that x power, well, okay, I am using the same, this is x. So, let us call this A and B. A B belongs to this. Suppose A is not here, B is not here, then A such that this is P plus A, and there exists M such that x power M belongs to P plus B. So, this would imply that x power n plus M belongs to P plus AB, which is P because AB belongs to P. Therefore, that is a contradiction because P is chosen, contradiction because P belongs to P sigma. That P belongs to sigma. Okay. So, therefore, this says that contradiction says that either A belongs to P or B belongs to P. This implies P is a prime ideal. So, P is a prime ideal in sigma implies that P does not contain x. So, what we have done is, if x is not a nilpotent, we have come up with a prime ideal which do not contain the given element. So, therefore, this implies that x is not in P, and that implies that x is not in the intersection of prime ideals. So, if x is not a nilpotent, then it is not in the intersection of prime ideals. So, this implies that the nil radical is indeed the intersection of all prime ideals. Is the proof clear? Okay. So, now what we have seen is the intersection of all prime ideals. Now, any prime ideal is a maximal, any maximal ideal is a prime ideal. So, what can we say about, can we say something about the intersection of all maximal ideals? Of course, this is intersection of ideals, this is again an ideal, okay, and this is called Jacobson's radical. It is the intersection of all maximal ideals. Okay. Now, is there a way to look at the elements or find the elements of this ideal? See here, to check whether an element is in the intersection of all prime ideals, if it is nilpotent or not, okay, that is a characterization. It is nilpotent if and only if it is in the intersection of all prime ideals. So, in this case, do we have something nice, nice characterization? So, let's look at, let's start with an element in the Jacobson radical. Now, so this is there in all maximal ideals. Now, if I look at, so this is says that x belongs to M for all maximal ideals. So, let us look at 1 minus x y. See, if this is, yeah. So, for any y in A, the element 1 minus x y, can it belong to M for some M maximal ideal? Because x y is x y belongs to M. Therefore, this cannot belong to M for any M. So, this implies that 1 minus x y is a unit in A. Yeah. Why is this? Because every non-unit is in some maximal ideal. So, here this is an element which cannot be in any of the maximal ideals. Therefore, it has to be a unit. So, if this is, so what we have proved now is that x belongs to Jacobson's radical of A implies 1 minus x y is a unit in A. Yes. Oh, sorry, does not belong for any M. Yeah. So, there is this natural question whether the converse is true. If this is a unit in A, can we say that for every y in A, for every y in A this is a unit, can we say that x belongs to maximal ideal, all maximal ideals? Suppose x does not belong to a maximal ideal, then this is A, right? Or in other words, that is, there exists some element u in M and r in A such that u plus r x is equal to 1, right, which implies that u is equal to 1 minus r x. But now our assumption is that 1 minus x y is a unit for every y in A, which means u is a unit by the assumption. That is a contradiction. U belongs to the maximal ideal M. So, this implies that x is there in all maximal ideal. So, that implies x is in the Jacobson's radical. So, what have we proved now? We proved that Jacobson's radical is the set of all elements x such that 1 minus xy is a unit for every y in A. So, Jacobson's radical is equal to set of all x in A such that 1 minus xy is a unit an immediate corollary of this is that if if 1 plus x is a unit for every x in M. So, let me write, let M be a maximal ideal and 1 plus x is a unit for every x in M. Okay. Let us see what could be the conclusion. Okay. So, 1 plus x is a unit for every x in M. So, I start with some non-unit. So, let y be some element of some non-unit in A. Okay. This will imply that yeah 1 plus, so x y belongs to M. See, if I multiply with any unit, if this is a unit and if I multiply with any unit, this will remain a unit, right. Now, if y is a non-unit, then 1 plus xy is in xy is in M, and that implies that 1 plus xy is a unit. That means, what does that mean? xy is in the x is in the Jacobson's radical, but we are starting with x in M. If I take in Jacobson's radical is intersection of all maximal ideals. Therefore, Jacobson's radical is contained in each maximal ideal, but here we are saying that M is contained in the Jacobson's radical, which means both are equal. This implies x is in Jacobson radical, and that implies M is equal to J of A, and that implies that A is a local ring. It has precisely one maximal ideal. Okay. We will come back to these properties as and when we go along. Let us look at some of the properties on ideals. You have seen that the operation taking the union, this need not be an ideal. When is this an ideal? I union j if one is contained in the other, right? It is if and only if. I union j is an ideal if and only if I is contained in j or j is contained in I. This is something that you have seen for the case of vector spaces, group theory, and yeah, at least in these two cases you must have seen earlier. This need not be an ideal, and this is an ideal if and only if one is contained in the other. Another interesting operation on I and j is I plus j. So, by definition this is set of all x plus y, where x is in I and y is in j. Then this is an ideal in A. Third one is I intersection j. The set of all x in A such that x is in I and x is in j. Again, this is always an ideal. Intersection of two ideals is again an ideal. Another operation that you have probably not seen so far in the vector space theory or group theory is Ij, the product ideal Ij. So, what could this be, or what should this be? X y such that x in I, y in j. Why? This should be the natural definition, right? Why is this? Why are you saying that this is not? Yeah. So if you define it like this, then this set is not an ideal. Okay. I will leave it to you to exercise. Find an example. Where will you look for? If you look at if you look for an example in Z, sorry, it's a PID. I'll leave it to you to experiment, try to get an example and show me that this is not an ideal. So therefore, this is not the way to define this. What we do is Ij, I define it to be set of all, or the ideal generated by this, or in other words, the smallest ideal that contains all these products. The product ideal is, as we saw, or as you should be seeing, if you take individual products, it does not form an ideal. So it is natural to talk about ideal which is the smallest and containing this one. I define to be that as my product ideal Ij. Is that clear? So Ij, I define it to be, so I can make a definition in many ways. Smallest ideal containing the set or this is equivalent to writing out the sets in the element like this, writing out the elements in the set like this, x y, where y belongs to J. Finite summation. This is, we are in the ring theory, and whenever I write sigma for summation, it will always be a finite summation, because we do not deal with infinite summation. So, there is a ring called power series ring, which has elements are power series, but the operation in that ring is summation, which we take only a finite summation. There is a difference. We will, I mean, I will take a power series as an example at some point of time, and I will probably deal with it. Okay, we will see. But whenever I write summation in this course, it means finite summation. Okay, this is the product ideal. Just to look at some quick examples. What is mz plus nz? This is GCD m comma n z, and mz intersection nz. This is, what would be this ideal? LCM of m comma n z. So, therefore, mz plus nz times mz intersection nz, this is mnz. So, in general, should we say I plus j times I intersection j is ij? Right, this is the analog. Should we? Z is a very beautiful ring, you know. So, we cannot expect everything that happens in Z to be true in general. So, this is whenever taking an example and trying to pose a general theory, Z is not a nice ring for that, because in Z lot of nice things happen which do not happen in other rings. So, this is not true always. So, again if you look for examples in Kx and Z are kind of very close ring property wise, both are PIDs, and you know, they are properties wise they are very close. So, therefore, if you look for examples in polynomial ring in one variable, again you will not be able to find it. So, try to think of an example so, when you are trying for an example, it should not be in Z, it should not be in Kx, okay. Yeah, so that itself should give you a indication. maybe I can even tell you, look for an example in k x comma y, polynomial ring in 2 variables. Okay. Now this is this holds true if I plus j becomes the whole ring. So let us see, suppose I plus j is the whole ring. Okay. In that case, see, when we write such a can you see one inclusion? Can you say that this is contained here? This is contained here. Which way is true? See, this is again this is a product ideal, this is a product ideal. So if I can say that every generator of this belongs to this one, then we are through. Now how does any generator looks like? X plus y times, let us say a, where a is in the, yeah. So I look at x plus y times a, then this is x a plus y a, x a is in I j, y a is in I j, therefore this is in I j, therefore the left hand side is contained in the right hand side. So I plus j times I intersection j is always contained in the product ideal I j. The question is, can we say that this is true? So suppose now this becomes clear, right? If I plus j is the whole ring, what is I intersection j? Sorry, what is this product? This product would be simply I intersection j. But this, if you take any generator of I j, it is of the form some product x y, where x belongs to I and y belongs to j. That product belongs to I as well as j, or in other words it is in the intersection, which means it is. Is that clear? So if I intersection, sorry, I plus j is this, the whole ring, then the left hand side is equal to I intersection j. But at the same time, I j is, this is always true, that is what we saw just now. Since I j is always contained in I intersection j, we have I plus j, I intersection j is equal to I j. Okay. So therefore, if I plus j is a, then we have this equality. Now if I and j sum up to a, then we say that the ideals are co-prime. If I plus j is equal to a, then the ideals I and j are said to be co-prime. So the terminology again came from the ring of integers. When you say two integers are co-prime, when there are no common prime divisors, or there you can their GCD is 1, or in other words, if you look at the ideal generated by so take two integers to be m and n, ideal generated by m plus ideal generated by n is the whole ring, and that is exactly what we have. Now, there is an interesting natural map. If I take ideals in A, if I look at the, see there is a quotient ring A mod I. Okay. If you have two rings A1 and A2, their Cartesian product is also a ring with addition and multiplication component wise. So, therefore, there is this is a ring, commutative ring, and what is its identity element? What is the identity element of this ring? 1 comma 1, right, or 1 bar comma 1 bar. Bar denotes the corresponding equivalence class. So, therefore, this is a commutative ring with identity, and there is a natural map from A to this ring. A to A mod I there is a natural map, and A to A mod j there is a natural map. Now, there is a natural map from A to A mod I cross A mod j, where any element x is mapped to x plus I x plus j. Now, what can you say once you have such a map, you start asking questions, right. What can you say about this? Is a natural map, this is a natural ring homomorphism. Okay. Can you say anything about the nice properties of what would be the kernel of this map? Kernel of this map is, so let us call this map phi. Kernel phi is I intersection j. Now, this is surjective, sorry, A to A mod I is surjective, A to A mod j is surjective. Now, can we say that phi is surjective? So, the question here is, given an element A plus I B plus j, can we find x in A such that x is congruent to A mod I and x is congruent to B mod j? See, think about this in Z. In Z, instead of I, think of let us say primes. If they are distinct primes, the Chinese remainder theorem says that you can do it. But so therefore, what should be the equivalent? If I and j are co-prime, so let's try to see. Suppose I and j are co-prime. Now, can we say that the map is surjective? Okay. So, how do I check whether the map is surjective? So, what should be the natural map? So, I have A, let A plus I and B plus j be in A mod I cross A mod j. I want to say that there exists an x which is in A mod I in A such that x is congruent to A mod I and x is congruent to B mod j. How do I look for that? See, there is already an information that x I and j are co-prime. What does that mean? It means I plus j is equal to the whole ring, which means there exists x in I and y in j such that x plus y is equal to 1. Bx is b minus by and ay is a minus ax. So, bx plus ay, this is b minus by a plus b minus ax minus ax plus by. Now, modulo I, what is this? Modulo I, this would be A is in, yeah, it will be so this is A plus A minus Ax plus B into 1 minus y. Modulo I, see this is in I, this is in I. So, modulo I it would be A. Similarly, modulo B, modulo J, I can write this as B minus By plus A times 1 minus x. So, modulo J it will be B. So, therefore, this is precisely the element. Ay maps to A plus I and B plus j. So, this implies phi is surjective. Now, I will leave this as an exercise to say that phi is, so this is the converse is also true. That is, if phi is surjective, then I and j are co-prime, and phi is injective or 1 if and only if that is trivial. I intersection j is 0, and you can do this is, we have done this for 2 ideals, this can be done for many, I mean n ideals, finitely many ideals. Okay. We will continue tomorrow.